Hello everyone, today we're going to go over section 2.3, which is getting information from the graph of a function. So we learned about functions 2 sections ago. Last section we learned about graphs of functions, and now we're really looking at how do we pull information when looking at the graph of a function. So as an overview, many properties of a function are just more easily obtained from a graph than the rule that describes a function, aka the actual function equation. So looking at the graph, we can get a lot more information than just the actual function itself, which is why we want to know how do we pull information from graphs instead of just from the function. So we see that in this section how a graph tells us whether the values of a function are increasing or decreasing, and also where a maximum or minimum values of a function are going to be. So really this section is all about also domain and range. So we're going to look at domain and range, when functions are increasing and decreasing, and how to find mins and maxes. So first off, values of a function and domain and range. We've talked about domain and range quite a few times now, at least definitely domain. But now we're looking at domain and range from a graph. How are we going to be able to tell what the domain and range is just by looking at a graph? So to analyze the graph of a function, you want to keep in mind the height of the graph is the value of the function. So whenever we're talking about a function and we're saying values of a function, we're talking about the f of x values, the y values, the range of your function. That's what we're talking about. So for domain and range of a graph, we say the domain and range of a function, y equals f of x, is obtained from a graph f as shown as the figure here. So this is our figure here. The domain is the set of all possible x values where f of x is defined. So wherever f of x is a valid function, wherever it exists, that's where your x values are defined. So your range in that case would be the corresponding y values. So when you write your domain is going from left to right. You are writing all the possible x values from the most to the left all the way the most to the right. So it's always one direction, just left to right, and it's basically the number line. So you're following the number line values. Range is a little bit different because range is going to follow from the lowest y value to the highest y value. It does not follow along with the endpoints of domain. It is always min to max. So in this picture that we see here, our range starts at the same place our domain starts, but our range tops out a little bit before the end of the domain because that's the highest value of your range, kind of this value right here, not the end of our domain here. That would not be the highest range value. So your range is going from the minimum y value to the maximum y value. Your domain is going from first to the end or left to right for the defined x values. So it's a little bit different for range than it is for domain. So as an example, let's just go ahead and look at domain and range. This example will be pretty quick. We will write something in our notes, but it will be very fast. So example 1, find the domain and range of the function f of x is equal to the square root of 4 minus x squared. This graph is shown below. So this is the graph of that function that we have there, and we want to know what's the domain and range of this function. Well, our domain, like we said, were all values of x that are defined in order from left to right. So if we look here at the x-axis, and remember we're going from left to right, we see on the left-hand side, the first defined point of x is -2. Then our function continues on, so we're going towards the right, and the last value on our right is 2. So our domain covers all values from -2 to 2. There weren't any holes in our graph or open circles or anything like that, but it does end at -2 and 2. And so we can say that it's defined at -2 and 2. So we're including -2 and 2 in this case. So our domain would have square brackets and it would go from -2 to +2. So let's just go ahead and write that in our notes really quick, just so we see kind of visually how that looks. All right, so in our notes here, number one, we have our function. I hand drew the lovely graph that you saw before. It's not perfect, but it has all the important parts to it. So what we're seeing here with domain, like we talked about before, that leftmost value along that x-axis there was -2, and the rightmost value on the x-axis is +2. And we include both since we don't have any open circles. If we don't have any open circles, we're just assuming everything is defined. So our domain will look like this. So we have -2 to 2, and we've included those values. So we drew in square brackets. Now, we want to look at the range as well, which we're just going to pop back over to our lecture to look at the nice picture, and then we'll come back to this really quick. So here we have the nice picture. Our range, remember, is from the minimum y value to the maximum y value. So we see that at these ends here, we see that the y value is 0. And at its highest point, the y value is 2. So our range is really only defined from 0 to 2, because this is the minimum value up to that maximum value there for our range. Let's go ahead and write that in our notes. So here we are, we just verified that our range is going to go from 0 to 2. And just like before, as long as we don't see any big open circles or anything like that, we can assume everything is defined. So in this case, our range is also defined at 0 and 2. So we would include brackets in this case as well. So, all right, that wraps up example number 1. So let's go ahead and head on back over to our lecture to continue. All right, so that was example 1. Now moving forward, we want to be able to compare function values. We want to solve equations and inequalities graphically, not algebraically. So starting off here with solving equations and inequalities graphically, we say the solutions of the equation f of x equals g of x are the values of x when the graphs of f and g are going to intersect. So whenever we have a function set equal to another function, in this picture here that's on the left, the solutions are the point where they cross each other. So the solutions of f of x is equal to g of x are the values of a and b. They are the x values. So the x values where those two functions cross each other, those are the solutions. So if you're solving for an equation, so when they're equal, it's the x values that mark those solutions there and where they intersect each other. Then if you go to the solutions of an inequality, such as f of x is less than g of x, these are going to be the values of x where your graph of g is higher than the graph of f. And we are talking physically higher. So if we look at this graph here on the right, we want to know what is the solution of f of x being less than g of x. So we have our graph here. We have the values of a and b again. We know these are when they're equal, but we want to know when is f less than g. And if we want to know what is f less than g, we are specifically looking at when is my graph of f below g. So in this case that we're looking at right here, our graph of f is physically and like spatially, visually below g. So f is less than g because it's under it. So that is going to be how we're going to solve inequalities. We are looking for which one is above and which one is below. The one that is below is less than, the one that is above is greater than. Then, since we have this strict inequality here, we don't actually include a or b because that's where they're equal to, and we wanted to know when is it strictly less than. So we would say that our solution of f of x is less than g of x is the interval from a to b where we don't actually include a or b because we don't include them since they're equal, not less than. So this is just an example of how we would actually solve equations and inequalities graphically. It is all about visual, no algebra, although you can always solve them using algebra as well. We're not trying to use algebra in this case. We're trying to visually decide what is higher, what is lower, what is greater than, less than, equal to, and those kinds of things. So, all right, let's go ahead and do example 2. Example 2, we want to solve the given equation or inequality graphically. So we have the same 2 equations in this case, and we're just testing different inequalities and equalities. So for part A, we have 2x squared plus 3 is equal to 5x plus 6. So we want to know, what are the solutions? Part B, we have 2x squared plus 3 is less than or equal to 5x plus 6. So we have that less than and equal to. Then C, we have 2x squared plus 3 greater, strictly greater than 5x plus 6. So, all right, we're going to go ahead and use Desmos and our notes to write out these different answers. But first, let's go to Desmos so we can graph these 2 functions. All right, so here we are in Desmos. We have our 2 functions graphed. We have 2x squared plus 3 here in red, and we have 5x plus 6 here in blue. So the moment we graph them, this is what it looks like. Like, okay, you know, we can see it cross here, but we assume, oh yeah, okay, it crosses again here. I don't really have that great of a view. So let me just try and zoom out. Okay, I can zoom out, but it's pretty far away. I'm still not getting a great view. So here's one way you can adjust your view. If you click on the graph settings here with the little like wrench, you can change your axes specifically however you want them. So let's go ahead. I'm going to pick for my x-axis. I'm going to go ahead and just do -5 to 5. I'm thinking, okay, this is going to give me a good look. All right, this is crazy. So we're going to change our y-axis to just go ahead and be, let's go with -1. And we're going to go up to, let's say, you know, maybe 30. We could probably even do like 25 if we wanted, but that's okay. We're going to keep it like this. So we rescaled our graph a little bit just so we have a much better view of what we're looking at, just because it's going to make everything easier. So here's our graph. We have 2x squared plus 3, 5x plus 6. And our first part for part A was we wanted to know, when are they equal? And we said that 2 functions are equal when they cross each other or when they intersect. So we see that our 2 graphs cross each other in these 2 points right here. If we're using Desmos and we want to know, hey, what are these values, we can actually just click. And there we go. Now we know what the values are. They are equal at these 2 points. But remember, our answers are the x values, not y values. So even though we have the 2 points that they're equal at, we only care about the x values. We want to know at what x values are these 2 functions equal. And they are equal when x is -0.5 and when x is 3. So we're ignoring these y values, these second values here. So let's go ahead and write this answer in our notes. All right, so here we are in our notes. Now we want to go ahead and just write out where they're intersecting. But remember, we're picking out those x values. So in this first answer here, we're going to say the graphs intersect, if I can spell, intersect at the points -0.5 and 3.5. And that's my symbol for and. I don't know, sometimes it looks a little funny. That's what I mean when I write that symbol, means and. And 3, 21. So that's where these 2 graphs intersect. This means the solutions are x equals -0.5 and 3. And remember, they correspond to the x values, we don't necessarily care about the y values. Of course, we care a little bit in the sense of what are they, but we don't care as far as the answer goes. So those are our answers for part A, negative 0.5 and 3. So now let's go ahead and do part B. We want to know, when is 2x squared plus 3 less than or equal to 5x plus 6? So let's go on back over to Desmos. All right, so here we are back at Desmos. And remember, what we're looking for is we want to know, when is 2x squared plus 3 going to be less than or equal to 5x plus 6? Now, if we're just thinking about the whole equal to included, so we want to know, when is the red graph less than the blue graph? But also, when are they equal? We know that they're equal at negative 0.5 and 3 at these points here. So now we're just deciding what interval are we picking for this inequality. We want to know, when is our red graph less than our blue graph? So defining these points again, if we want to know when the red graph is less, remember, we're looking visually. We want to know, when is the red graph below the blue graph? So if we look at our graph here, we see that if we took, a straight line, let's say, x equals a, and we can use this as a slider, typically. I don't know why it said that, but normally you can write in, maybe let's try C. Nope, didn't work either. Sometimes it'll let you add a slider, but I guess it's just not letting me right now. But normally, if you have a straight line, and you're looking at it, whichever graph is going to have that higher value is the one that is greater, the one that is above. So if we had a straight line, and let's just actually just pick a real number, let's say x equals 1, we see that the blue graph is above the red. Its value is 11, while the red graph only has a value of 5 when x is 1. So in this case, we're seeing that, yes, 2x squared plus 3 is less than 5x plus 6 on this spot right here, which is between negative 0.5 and 3. So what we're seeing here, and this is consistent throughout this entire interval, is that our red graph, 2x squared plus 3, is less than or equal to, on the interval of negative 0.5 to 3, including negative 0.5 and 3. So let's go ahead and write that out in our notes. All right, so here we are in our notes. We're going to go ahead and write out, we're going to say the graph of 2x squared plus 3 was below the graph of 5x plus 6, that's a 6, there we go, between the values of x equals negative 0.5 and x equals 3. This means the solution of the inequality is going to be the interval between those two x values. And we're going to include those x values because our inequality is less than or equal to. So we're going to have square brackets, negative 0.5 to 3, and our square brackets there. So that would be our answer to our inequality for part B. So let's go ahead and head back on over to Desmos to answer our last question, which is, when is 2x squared plus 3 greater, strictly greater than 5x plus 6? All right, so here we are back at Desmos, and since just by kind of a process of elimination, we can pretty much guess where 2x squared plus 3 is going to be greater than 5x plus 6. But, once again, looking at our graph here are our intersection points where they are equal. We know that between these x values, our graph of 2x squared plus 3 was less than 5x plus 6, meaning that the red graph was below the blue graph between these x values. So what does this mean? outside of this interval right here is probably going to be the opposite. We see the red graph being above the blue graph on the outside of those values. Let's go ahead, let's put some more, vertical lines here to represent this a little bit better. Let's put it at x equals -1 and x equals not a negative. Let's go with x equals 3.5. Should be able to kind of get it in our frame here. Let's pick some different colors. Let's not have red and blue again here. So we'll go with green and purple. All right, so we see that on these two x values, yes, our red graph is above our blue graph. In both cases, we're going to assume that in both infinite directions, this is still going to be true. So what we see here is that starting at this side, and we can zoom out a bunch of times to see that this is always going to be true. So we're always going to assume now in this case that starting from our smallest number, we can think of -infinity, up to the x value where they intersect, because remember that is when they are equal. So from -infinity to the x value -0.5, our statement is true. 2x squared plus 3 is greater than 5x plus 6. And we will not include the x value of -0.5 because it is a strict inequality. But we also have another side of our inequality here as well. We have going from 3 to positive infinity, same thing. 2x squared plus 3, our red graph, is above the blue graph 5x plus 6. So we have two intervals where this inequality is true. Since we have two intervals and we just want, one answer, we're going to slap a union in between those two intervals and call it a day. So let's go ahead and write out that answer in our notes. All right, so let's go ahead and write this out. Once again, we're going to write a little explanation. We say the graph of 2x squared plus 3 was above the graph of 5x plus 6. I wrote b again. I don't know why I did that. 5x plus 6 for x less than -0.5 and x greater than 3. So this tells us that the solution of the inequality is going to be -infinity to -0.5, because we said it's all the way from -infinity up to that value when they're equal, not including -0.5. And so we're going to write that union 3 to positive infinity. So everything has parentheses. We have a union connecting those two intervals, and that would be our solution there for part C. So that is how we would visually go about solving these types of equations and inequalities without doing really any algebra. So, all right, that wraps up example 2. Let's go ahead and head on back over to our lecture. All right, that was example 2. Let's go ahead and keep going. So next we have increasing and decreasing functions. So our book definition here, we say that if f is increasing on an interval I, so some random interval, if the y value of some x sub 1 value is less than the y value or f of x value of some x sub 2 value, where x sub 1 is also less than x sub 2 in your interval, that means it is increasing. So we're basically saying here that if this x sub 1 is less than x sub 2, f of x sub 1 should be less than f of x sub 2. If we're looking at this graphically, it's going up. We're looking at it. We're always reading our graphs from left to right. So in this case, if it's going upwards as we're looking from left to right, that means that It is increasing. We're going, up the mountain, we're going up the roller coaster, we're not going down. So we're always looking from left to right. That is key here. Left to right, we're going up that roller coaster. F is increasing. So we're saying that as x increases, y should increase as well, or f of x should increase as well. Then our second here, opposite, f is decreasing on an interval I if f of x sub 1 is greater than f of x sub 2 when x sub 1 is less than x sub 2 in your interval. So fancy words of saying if x is increasing, your function is decreasing if your y values are going to be decreasing as well as x is increasing. So as x is still increasing, because remember we're always reading from left to right, x is always increasing, we're saying our y values are decreasing as x is increasing. But also if we're looking at our function in order from left to right and we look at our graph and it's going down, we're going down that roller coaster, it's decreasing. So I'm sure you all have a general understanding of what increasing and decreasing mean in general outside of math. So you're just applying that to what it looks like here. You're going up a roller coaster or down a roller coaster as you're looking from left to right. That will tell you if you're increasing or decreasing. So, all right, let's go ahead and do our next example. This should be a pretty easy one. We're gonna just kind of talk our way through it and then we're gonna write out our answers in our notes here. So example 3, we have the graph below gives the weight W of a person at age X. We want to determine the intervals on which each function W is increasing and when it's decreasing. We're also going to have areas where there is no change, and we're going to write that out as well. But we're just looking at when is it going up, when is it going down, and when was there no change at all. So if we look at this function, and remember always reading from left to right, so we start at 0 and we're going to end around 80 here. We're just going to say when it is increasing and decreasing, then we're just going to write our answers in our notes. So from the beginning here, starting at 0, we see, we're climbing here. Our weight, we're going 50, 100, 150, ending probably around the age of about 25 here. So since our weight was growing as our age was growing, our function was increasing. We are riding our little roller coaster up. It's very suspenseful. We're having a great time. So we were increasing between 0 and say about 25. Then we see between the ages of 25 and 35, we have this plateau. We stay around 150 pounds. So no gain, no loss. We were just sitting here with no change. So that's what we'll say had no change. Then between the ages of 35 and 40, we see another little increase here. So from 150 up to 200. So with the increase of about 5 years, we had an increase of about 50 pounds as well. So when X increased, Y increased, which means we had a function that was increasing. So our function increased again between 35 and 40. Then between 40 and what looks like about 50 here, we see there was a little bit more gradual, but a decrease. So we said this decrease, so as our age increased still, we had a decrease in our values of y, which means our function was decreasing. So our function decreased between the values of 40 and 50. So remember, our y values really don't matter, just in the sense of being able to actually read the graph. They help us, but the y values are not going to go in our answers anywhere. So then lastly, real quick, between the ages of 50 and 80, it looks like there really wasn't any change. There is maybe, some debate. Maybe it looks like it's going up a tiny bit. I don't think so. We're going to say it's no change. So between the ages of 50 and 80, we had another plateau. There was no change in the weight. So we say that there was no change. So all right, let's go ahead and write all of our answers down in our notes. All right, so we're going to go ahead, copy down what the different intervals for increasing, decreasing, and no change were. We just went over this, so we're just going to write the intervals. So we said that our weight was increasing between the ages of 0 and 25, and also it increased from 35 to about 40. A slight note when it comes to writing intervals of increasing and decreasing, there is quite a bit of debate in the mathematical community about whether or not you should use parentheses or brackets. And really, it doesn't have that much effect on your answer. So typically, I'll normally write parentheses, but if you wrote brackets, it should be acceptable as well. I do believe WebAssign likes parentheses and not brackets. So if your homework, that might, help a little bit with troubleshooting. But typically, we're going to write parentheses, but if you wrote brackets, it really isn't that big of a deal. It doesn't matter that much. But all right, so back to decreasing, we saw that our person here had a decreasing weight between the ages of 40 and 50. And that was it. There was only one interval. And then lastly, we saw that there was no change between the ages of 25 and 35. And again, between the ages of 50 and 80. So there we have it. That's how we would write out where our intervals were increasing and decreasing for our given graph. So let's head back on over to our lecture. All right, so that finished up example 3. So this is the last concept of our section. We have local maximum and minimum values of a function. So these definitions are very wordy, I guess you could say, from the book. So these definitions are from the book. We're going to read through them, and then I'm going to tell you how to find local maximum and minimum values of a function in a much, much, much easier way. But so here we go, definition from the book, local maxima and minima of a function. First of all, just understand the word local just means wherever you're looking. It just means that there is no one singular maximum, one singular minimum. You are just counting all of the maximums and all of the minimums. That's why we use the word local. So number 1, we see a function value f of a is a local maximum value of f if f of a is greater than or equal to f of x when x is near a. This means that for f of a is greater than or equal to f of x for all x in some open interval that contains a. In this case, we can say that f has a local maximum at x equals a. Now, if you didn't quite catch that, perfectly fine. We're going to do the second one real quick though. The second one, we see the function value f of b is a local minimum value of f if f of b is less than or equal to f of x when x is near b. This means that f of b is less than or equal to f of x for all x in some open interval containing b. In this case, we can say that f has a local minimum at x equals b. Okay, yes, very wordy. Not great definitions, to be honest. So if we're looking for local maximums and minimums of a function, and let's say we're given some function like this. We see this graph, the one that's kind of above here, and our graph has hills and valleys. We see the hills are where we go from increasing to decreasing, and our valleys are where we go from decreasing to increasing. The valleys are the lowest points on curves. The hills, the maximum points, are the highest points on the hills. So our maximum values are always the highest value on a hill or a mountain. Sometimes we say mountain. So on a hill or a mountain, that highest point is the maximum or a local maximum. And the lowest point in a valley is a local minimum. And it doesn't matter how many valleys or how many hills you have. Each highest and lowest point is a maximum and a minimum. So that's why you can have multiple. So in this case, we have 2 maximums and 2 minimum points here. That's what these very fancy, very wordy definitions are really trying to get at. They have lots of very technical terms. But so if we look at this bottom graph here, we get a little bit of another look here. So our local maximum and minimum points, they are located at values of x. They are located at x values. But if we want to know what is the actual maximum value, that maximum or minimum value is y, because the value is how high or how low is it, not where is it located. So a maximum value would be that maximum y value. A local minimum value would be that low y value. So that is the difference. You want to know the difference between where and how much. where is X? How much is Y? So now it comes into play where it is going to be important to know what the value of Y is, not just X. So that's going to be important to us for finding local maximums and minimums and their values. So let's go ahead and do an example. This is a long example, but we're going to use Desmos, so it's going to make it a little bit easier. So example 4, we have a word problem. We have a highway engineer develops a formula to estimate the number of cars that can safely travel a particular highway at a given speed. She assumes that each car is about 17 feet long, travels at a speed of X miles per hour, and follows the car in front of it at a safe following distance for that speed. She finds that the number n of cars that can pass a given point per minute is modeled by this function. N of x is equal to 88x divided by 17 plus 17 times x divided by 20 squared. We're plugging that into Desmos, so don't freak out about it. But we're going to graph the function in Desmos, and we're just going to determine the intervals where our function is increasing and on which intervals it is decreasing. And part B, we're going to find the maximum value of n and what is the maximum carrying capacity of the road, and then also what speed is that going to be achieved. All right, so let's head on over to Desmos to graph this function and then be able to answer these questions. All right, so here we are in Desmos. The screen was pretty much set the same as we saw in the last one. So the moment we type in this function, this is what it looks like. It's not that great, but let's go ahead, zoom out a little bit. Okay, this gives us a better idea of kind of what our function looks like. So we're going to adjust our settings to make sure that we're getting the best possible kind of image here that we want. So we see that, we kind of have the max point here dangling around 50. Let's say that we're going to go from 0 to 60 for our y-axis. It wouldn't make sense to have any negative values for the context of this problem, so we can start at 0. And for our x-axis, we also don't want to have any negative numbers for our x-axis either, because it also wouldn't really make sense. And then we'll keep it at about 80. That looks okay. And we'll just pull it a little bit over here so we get, those numbers included. But so what we're seeing here is that we have speed as x and these the y values as n, or the carrying capacity, the number of cars. So our questions, if we remember for part A, we want to know when is the function increasing and decreasing. And B, our question was, what is the maximum value? What is the maximum carrying capacity? And then what is the speed at the maximum value? So we've got a few things that we're going to solve for, and you never have to solve, anything in order necessarily. It's actually a little bit easier to solve part B and then solve for part A. So for part B, we want to know what is the maximum value. So if we look at our graph here, our maximum value, remember, we're looking for the highest point on the hill. So we see our function increases and then it stops and then it decreases again. So we have a hill here, and the highest point on the hill is the maximum value, which if we click on our graph is right there. The maximum value is the y value. So our y value in this case is 51.765. So our maximum value is 51.765. We want to know what speed is the maximum value achieved. The speed is that question, where? Where is the maximum value? And the answer to that question is the x value, 20. So the speed, when speed is 20, we have the highest number of cars that can pass through, which is 51.765. So let's go ahead and write that in our notes, and we can answer that last question for part B as well. All right, so for part B, we said that maximum value was 51.765. That was the maximum value. And this was n of x. So we can scoot that over a little bit. So when n of x was 51.765, that was the largest value we had. And we said that its speed at that maximum value was 20. So the speed was x equals 20. That was where it's located and what the actual maximum value was. Now the last question here was, what is the max carrying capacity? So our number is 51.765. We're just going to round to the next closest number, which is going to be 52. So our maximum carrying capacity is going to be about 52, and they are in cars. So we have about 52 cars. We're going to write about 52 cars, and we'll throw in at a speed of 20 miles per hour. So there we go. We've answered our question for part B. Now our question for part A was we wanted to know when are we increasing and when are we decreasing. So let's go ahead and look at Desmos one more time. So since we answered part B already and we're looking at the graph here, we can pretty much just safely assume what we know is the increasing and decreasing intervals. But if we look at our graph here, we see that reading from left to right, from 0 to 20, our graph is increasing. Our y values are increasing, which means that our graph itself is increasing. We are riding up this roller coaster right now. So for our answer for increasing, we have from 0 to 20. Once again, remember, negative numbers just don't really make sense in this concept. You can't have a negative speed, so we wouldn't include any negative numbers. We would include 0 to 20. Then we want to know, okay, when is it decreasing? It's decreasing after 20. Now, how high it goes, we don't really know. We can safely assume that there's probably definitely going to be some upper speed limit, but we don't know exactly what that speed is. We weren't really given a maximum, so we're just going to say infinity. Obviously, there aren't any cars going insanely fast, but for the concept of our problem, we're just going to throw in infinity. Negatives don't make sense, but infinity does somehow. So that's our answer. We're going to say it's increasing from 0 to 20 and decreasing from 20 to infinity. So that's what we're going to go ahead and write. Let's write that in our notes and finish up our problem. All right, so we said our function here was increasing on the interval 0 to 20 and decreasing from 20 to infinity. So, all right, that finishes up our problem number 4. So let's go ahead and go back over to our lecture. All right, so just finished up example 4. That wraps up section 2.3. So in section 2.3, we covered domain and range, solving equations and inequalities graphically, increasing and decreasing functions, and local minimum and maximum values. So, all right, that wraps up that section, and I'll see you in the next one.